Good afternoon, everybody.
Hi, Professor. Good afternoon.
Hi, how are we doing?
Pretty good.
All right. So hope you had a nice long weekend, and we're back for chapter 24 or chapter 23 if you're using the 10th edition. I'm assuming that you have had a chance to study Gauss's law, right? So what I will do today, just following the same scheme as last time, we're going to start with a summary of a one-page summary, or rather half a page summary of chapter 23/24, just to make sure it's a checklist for you to make sure you understand all the major topics in this chapter. And then we're going to talk about a couple of sample problems not included in a video lecture. And of course, answer any questions you have. And after that, we want to discuss this week's lab, which is Gauss's law. Okay, you can interrupt me anytime you have any questions. This is a perfect time to ask me questions. Some of you have been using my office hours quite well, by talking with me extensively about how to solve certain problems and whatever. But not everybody's doing that. Maybe you want to talk to me, during the lecture and ask me questions, which is also a good time. So please make sure you do that. Okay, you can always talk to me. You can always interrupt me because we do have time. Because we're not actually finishing the lab during the meeting time, so we have plenty of time to do discussions. Okay, so let's get things started. I'm going to share screen with you for the summary. So here's a summary. Here's a half-page summary of chapter 23/24, Gauss's law. Okay, so you already know by now. I made some advertisement about this chapter just to get you interested, and I said that you can rewrite Coulomb's law in a new form to highlight the uniqueness of the inverse square nature of the force, and by doing so, you can find better ways to solve certain problems of the electric field when there's high symmetry. And you already saw what I meant by that, and that is to rewrite Coulomb's law in terms of Gauss's law. So Gauss's law is a mathematical variation of Coulomb's law. Okay, you can derive one from the other. But Gauss's law, in a derivation, you can see clearly that without the inverse squared nature, you don't have Gauss's law. So inverse squared nature is really mathematically unique, because with any other power dependency, all to the power n, unless it's n equals -2, you cannot have Gauss's law. Okay, any other index doesn't matter, but -2 is a special number. And that's what leads to Gauss's law. So about Gauss's law, the first thing you want to know is the definition of the electric flux. Okay, so we're rewriting Coulomb's law in a totally different form by introducing the electric flux, which is the integral of E and dA, the dot product E and dA, and integrate over that. You might think that we're just making things harder than it should be, because the original Coulomb's law has no integral in it, right? It's an elementary form, but now we're making it sound more complicated by writing an integral. Well, we don't want to make things more complicated than it has to be. But the thing about the original Coulomb's law is that, it's not easy to use Coulomb's to solve for electric fields of, say, a uniform sphere, right? Uniformly charged sphere. You know how hard that will be if you try to use Coulomb's law to do that. It's a three-dimensional integral that you have to do. So it's limited when it comes to finding certain electric field of certain charge distributions. So, but by rewriting it in terms of Gauss's law, we can take advantage of the symmetry of the problem. So that's why we're doing that. That was the motivation. And then please also make sure you understand the three-step proof of Gauss's law. We have three steps, right? First step is to prove Gauss's law in a special case, which is what? A single point charge at the center of a Gaussian sphere. Right? Why a sphere? Because a single point charge exhibits spherical symmetry. The electric field lines produced by a single point charge radially outward or inward, but spherically symmetrical. Okay, so it's very easy to prove Gauss's law in this very special case. And from this very special case, you already know the special nature of the inverse squared law. Because as we grow the Gaussian sphere, let's say we double the Gaussian sphere, so the radius becomes 2r instead of 1r. The area grows by a factor of 4, right? And that's geometry. That's nothing to do with physics, because the area of a sphere goes like r to the power 2, r being the radius. But at the same time, the strength of the E field decreases by a factor of 4. Now that is physics. That is Coulomb's law, inverse squared nature. So the area grows by a factor 4, but the electric field decreases by a factor 4, and the product of E and A remains the same, right? So you combine physics with geometry, you find that for this special case of inverse square law, the flux of a point charge through a spherical Gaussian surface does not depend on the size of the sphere. You can double the area of the sphere and you find the flux to be the same. Okay, it's very simple, yet it already shows why the inverse squared nature is unique. And the next step is to prove that it's not just valid for a point charge with a spherical Gaussian surface. It is valid for any shaped Gaussian surface, as long as you have only one point charge as the source. Okay, that second step is a little bit more involved, but we did that. Remember how we did that? Okay, so make sure you understand that. Basically, we just extend a cone from that point charge. That cone will intercept two surfaces. One, the original sphere. The second one is the new arbitrary shape. You want to prove that the flux through the two intercepted areas by the same cone are equal to each other. Okay, that's the second step. The third step is also rather simple, and that is you go beyond a single point charge as a source. You can have a whole bunch of charges as a source, but since each point charge satisfies Gauss's law, you can add all these equations up using the superposition principle. You find it also valid for multiple charges, not a single charge. So these are the three steps. Make sure you understand these three steps. Okay, the first step is the simplest step, but it's also the most crucial step, because that is where you see the area growth cancels with the diminished strength of the electric field due to the fact that the force is 1 over r squared. Okay, this is not only true for Coulomb force, it is also true for gravitational force, because the gravitational force also satisfies inverse squared nature. Okay, so Gauss's law is not only valid for electric force, it is also valid for the universal gravitational force. So there is a Gauss's law for gravity, from which you can easily prove Newton's shell theorem. Okay, now if you took 1B, some of you actually went through the derivation of the Newton shell theorem using calculus. That was complicated, right? If you took my 1B, what I told my student was, let's not do the proof. Let's just trust Newton for now. Okay, but when you get to 1C, we look at a different part of physics, which is E and M. You will see that there is a very elegant way, simple way to prove Newton's shell theorem, which is Gauss's law. Okay, so that's one nice thing about looking back at the gravitational force, and you can see these two seemingly unrelated forces share this very important common feature, and that is a strong hint that these two forces may be related at a higher level. Okay. But how are they related? Nobody knows for sure. It's one of the fundamental mysteries of nature. All right, now, so that's Gauss's law, how we proved it. And then we're gonna start using Gauss's law, right? And there are two major applications. One is electric field of highly symmetrical charge distributions. The other is ideal conductors. With an ideal conductor, you don't need any symmetry. You can still use Gauss's law to find solutions. Okay. When it comes to high symmetry, there are only 3 types of symmetries which allow for simple calculation with Gauss's law: spherical, cylindrical, and planar. I mean, there are other symmetries such as axial symmetry. Okay, for example, remember the sample problem in the first chapter? You have a ring of charge, right? A ring of charge, and you want to look at the electric field of a point on the axis of that ring, right? Now, because of the symmetry, we know the electric field is points along that axis, either away from the ring or towards the ring, right? That's called axial symmetry. And that is, if you rotate the ring about this axis, nothing happens, the field remains the same. But this symmetry is not high enough for us to use Gauss's law to solve for the electric field. It doesn't mean Gauss's law is wrong. It's just that it's useless. It doesn't give you the electric field easily. The whole point of using Gauss's law to solve electric field of high symmetry is that Gauss's law says you can think of any Gaussian surface of any shape. As long as it encloses the same amount of charge, the flux through that surface is the same. And that is equals Q enclosed over epsilon naught. Remember that. Okay. And that, by the way, also explains why people defined K as 1 over 4 pi epsilon naught. You wonder why 4 pi? I mean, what's the deal with 4 pi there? Well, it's because that way Gauss's law becomes very simple. There is just Q over epsilon naught. Imagine if you don't use epsilon naught, okay, epsilon naught is 1 over 4, I mean, epsilon naught itself is 1 over 4 pi, 1 over 4 pi k, right? So you can rewrite Gauss's law as Q enclosed times 4 pi k. So there's a 4 pi there, okay? But if you include that 4 pi in a definition of epsilon naught, you don't need that 4 pi on the right-hand side of Gauss's law. It's a matter of convenience, but there's a logic behind it. Okay, going back to the case of symmetry. Since Gauss's law can allow for any Gaussian surface, you can draw the Gaussian surface according to the symmetry of the problem. For example, if you have a spherical charge distribution, could be a single point charge, could be a uniformly charged sphere, a solid sphere, could be a uniformly charged spherical shell of any thickness, doesn't have to be zero thickness, okay? Then no matter what, all of these fields have something in common. That is, the field lines are radially outward or inward. That's one thing. And also, if you draw a sphere centered at the center of that charge distribution, then anywhere on the surface of that sphere, the electric field must have the same magnitude. Okay, that's spherical symmetry. Because of that, why don't we choose a Gaussian surface, which is a sphere, which reflects the symmetry? You can choose any Gaussian surface you want, might as well choose a sphere. And that greatly simplifies the integral on the left-hand side of the Gauss's law. So E dot dA just becomes E times A, okay, just simple as that. You know, just E times A. So you don't really you're not dealing with an integral because the integral has to be easily worked out, okay? It just move A to the other side, that's all you have to do. Okay, so you can find E, just like that. You don't have to integrate, cut it into small pieces to integrate. It becomes unnecessary, right? That's spherical symmetry. For cylindrical symmetry, same idea. If you have a very long line, for example, uniformly distributed charge, a very, very long straight line, you know the electric fields are cylindrically symmetrical, right? Radially outward, perpendicular to the line, right? So because of that, this time we can use a Gaussian cylinder, to enclose part of this source, okay? And then anywhere on the surface of that cylinder, because of symmetry, the E field has the same magnitude and it's radially outward, assuming lambda is positive. Okay, that way, again, the electric field on the side would simply be the area of the side times the electric field itself. But the flux is just E times the area of the side, which is 2 pi r times the length. That's it. Okay, so you don't have to work out this integral, from scratch. You can take that E field out from the integral because of the symmetry. Okay, so similar to that, you have planar symmetry. This time we just draw a box with surface, top and bottom surface parallel to that plane, which contains the charge. So anyhow, the idea is the same for any of these three symmetries, is to draw a Gaussian surface in the shape of the symmetry, either a sphere or cylinder or box, depending on which shape it is. And then you can greatly simplify the integral, just taking that E out because E is uniform on that surface. Okay, that is only true for one of these three symmetries. For axial symmetry, you don't have that. You cannot draw any Gaussian surface. If you draw a cylinder with that axis in the middle, the problem here is that on the surface of that cylinder, the E field is not uniform, okay? It depends on where you are, right? How far you are from that ring, right? So you cannot simplify it as E times the area. You cannot do that. E is not uniform on the surface of that cylinder, okay? So that's the idea of using the Gauss's law to solve for electric field of highly symmetrical charge distribution. These are the only three symmetries that allows you to do that. Okay, any other symmetry is not good enough. It's not high enough. So Gauss's law is powerful when you have these three symmetries. But outside these three symmetries, it is still valid, but it's not that useful. Okay, in the integral form, it's not that useful. except for one special case, that is ideal conductor. In the case of ideal conductor, you can draw important conclusions from Gauss's law without any symmetry. So what's an ideal conductor? It's a material which can conduct electron flow without any impedance. Okay, so you got loose electrons just swimming around, okay, in the conductor, and anytime there's any electric field at the location of those electrons, which is inside the conductor, the electron will start to move. The electron being negative charge will move against the direction of the electric field. Okay, any field that's non-zero will cause the electron in that place to move, and that will not stop until the field becomes zero and the electron starts moving. Okay, so any field that originally you may have is quickly neutralized by the motion of these electrons, because as the electrons move against the electric field, they cause their own electric fields, which will neutralize the original field. So eventually the total field becomes zero, because until that happens, the electron will continue to flow and flow and flow until the field is neutralized. And that process is very fast. We're talking about nanoseconds. Okay, you have an electric field somewhere, right? You put a conductor in that region. Initially, the field inside the conductor is not zero. That causes the electrons to flow. But the electrons flow so fast that within a matter of nanoseconds, the game is all over. The electron, after they move, they will cause a redistribution of the charges so that the total field inside the conductor becomes zero. Then the electron will stop moving. Okay, the total field becomes zero. The electron stop moving. So you can safely say that there's no electric field inside the solid part of an ideal conductor. Solid part means this is where you have electrons. Okay, I'm not talking about a cavity. If it's a cavity, you can have a field inside a cavity because there's no electron there in the cavity, it's vacuum. So in principle, you can have a field if you have a conductor and there's a hole in that conductor. Is there any field inside that hole? The answer is we don't know. It's possible, but on the solid part of the conductor, where it's meat, so to speak, okay, you cannot have electric field because electrons will start to move in that region. Okay, so that is the first thing that comes to mind when it comes to ideal conductors, and that has nothing to do with Gauss's law, by the way. It's just the nature of the ideal conductor. But with that in mind, okay, with that first condition in mind, plus Gauss's law, you can draw important conclusions. Okay, as we argued in the lecture and also in the textbook, because of Gauss's law plus this first condition that's equal to zero inside, you can argue that there is absolutely no loose charge inside any ideal conductor, the solid part of the ideal conductor. You cannot, for example, have an isolated positive charge somewhere inside or isolated negative charge somewhere. It's just not possible. Okay, if you charge a conductor, if you give it some extra charge, positive, negative, the only place they can go is the outer surface. They cannot live somewhere inside. Okay, that sort of makes sense. You think about it. In an ideal conductor, charges can flow freely without any impedance. So suppose I put some positive charge in there. Okay, I charge this conductor with some positive charge. Positive charges do not like each other. So what happens? They try to push each other away. Right? They want to get away from each other as far as they can. So they're going to move away from each other until where they're stopped by the border of the conductor. They got no other place to go. They are stopped by the physical border of the conductor. And that's why they end up on the outer surface. Okay, so it actually makes sense if you think about it. Okay, all right. So I have a question here. You mean a conductor can be deduced by integrating the electric field? By integrating the electric field, what do you mean by integrating the electric field? I'm not sure I get what you mean. Perhaps we can discuss that individually if you want to, or if you actually want to explain that to the class what you mean. Conductors, the conductor can be deduced by integrating the electric field. I do not quite understand that. All I want to say is that if it's an ideal conductor, there is no electric field in the solid part of the ideal conductor. And that will lead to the conclusion that no loose charge can live inside the solid part of the ideal conductor. Otherwise, you're going to violate Gauss's law, as we saw in the video lecture. Okay, so it can only live on the outer surface, and so there could be a charge distribution sigma on the outer surface. And moreover, Gauss's law can be used to figure out the electric field right outside the conductor. I know inside is 0, right? But right outside, what is the electric field equal to? It's sigma over 2 epsilon naught. That requires no symmetry. As long as you are very close to the outer surface, you're just outside the conductor. Okay, the electric field is always sigma over 2 epsilon naught. Using Gauss's law, you can show that. Okay, so again, with ideal conductors, you do not need symmetry to draw these important conclusions. Okay, so once again, in a nutshell, what did we learn in this chapter? Coulomb's law can be rewritten as Gauss's law. Okay, Gauss's law can be used to solve electric field of these 3 symmetries or draw important conclusion for ideal conductors. Okay, so that's the summary of this chapter. Okay, any questions? All right, I'm going to post this document for you. So when you read through this document, pause at every entry. You read electric flux and you close your eyes and say, electric flux, do I understand what it means? Okay, 3-step proof. Do I remember what these 3 steps are? So, make sure you understand. Then you read the next one. If you understand each and every item here, you're pretty much covered for the content of the chapter. Okay? So if you don't have any immediate question at this point, let's move on to the next one. And next one is I am going to talk about a couple of sample problems. Okay. So let me share a screen with you again. This time I'm going to use, I want to be able to write something on it. So hold on one sec. Okay. Screen share, new screen share. All right, screen mirroring. Okay, can you see it?
Yes.
Okay, good. So, so I'm going to go over a couple of sample problems. These problems have been used as my midterm problems before. Okay, and they're not entirely new. Some of you may have seen it, but in the video lecture, I pretty much talked about all 3 symmetries. But in a case of a sphere, for example, I only talked about the case of a solid uniformly charged sphere versus a spherical shell. Okay, but here we have a little bit more complication. I have a solid sphere in the middle, insulating solid sphere, and I have a spherical conducting shell of a certain thickness outside. Okay, both are charged. This guy is charged to Q. This guy is also charged to Q. They don't have to have the same Q, but just by chance they do. Can you find the electric field anywhere, everywhere? That's a function of R. Okay, so start from center. How do you find the electric field of the solid part? By the way, it's an insulating sphere, okay, with uniform charge distribution. Let me ask you this question. If this is a solid conductor, not insulator, is it possible to have a uniform charge distribution inside? Anybody? Would that be possible?
No.
No, why not?
Because inside there wouldn't be any electrical field.
Yeah, there cannot be any field in any charge inside. Okay, so where would these charges go if it's a solid solid conductor? What would that Q be at?
On the surface.
It has to go to the outer surface. That's right. Okay. So when I give you, I say it's a uniformly charged sphere, you must have something in mind, and that is it's got to be the insulator. Okay. If it's a conductor, remember you got all these positive charges, right? They don't want to be close to each other. They want to get away from each other as far away as possible, so to keep on flying away. Okay, until they reach the outer surface, they got no place to go. They have to stop. They have to stop escaping. Okay, and that's where they end up. All right, with a solid, with an insulator, the charges cannot move. They're immobile. They're tight. Okay, so that's why you can have a uniform distribution. So anyhow, how do you calculate the electric field inside this part between 0 and A? How would you do that? Well, it's spherical charge distribution. So therefore, I'm going to draw a Gaussian sphere like this, right? And I will find the electric field by finding the flux. And then the flux will be equal to the charge enclosed divided by epsilon naught. Okay, so we did that, and you recall. Let me write some briefly. Okay, so the way we do that between 0 and A. I would just draw a Gaussian surface, centered at point O, right? And then I have this E dot dA on that surface, and that will be equal to the first step is just E dA, because I know the electric field and dA, they're both radially outward, so E and dA have, as two vectors, they have the same direction, so E dot dA is just E dA. And secondly, E, here is just the magnitude of E. The magnitude of E is the same everywhere on the surface because of symmetry. So I can take that out of the integration. That's just dA, right? And then thirdly, dA, the integral of dA is not just the area of a sphere, is 4 pi r squared. So it's E times 4 pi r squared. And what is that equal to? Q enclosed over epsilon naught, right? Q enclosed over epsilon naught. And all I have to do now is to solve for E, then move the 4 pi r squared over, and that's all I need to do. Hold on one sec. Let me. Okay, right? So E is equal to Q enclosed over 4 pi epsilon naught r squared, and then 1 over 4 pi epsilon naught, that's just K. So you can write this K, Q enclosed over r squared, and you can see clearly that this is just the electric field of a point charge. Isn't that the electric field of a point charge, right? And what is the magnitude of this point charge? It's a charge enclosed by the Gaussian surface. Okay, that in fact is part of Newton's shell theorem. Newton's shell theorem has two parts. Part one is the gravitational field outside a uniformly charged, a uniform spherical mass. What is the gravitational field equal to if you're outside a uniform spherical mass? It's equal to the field produced by a point mass located at the center of that sphere. So for the Earth, the mass is big M. You are on the surface of the Earth. The radius of the Earth is R. What is the magnetic field? What is the gravitational field there? G times mass of the Earth divided by R squared. Because look, it's just the same as the field of a point charge. Here is a point mass for the gravitational field. Okay, so that's that. Of course, it's just a matter of how you calculate this charge enclosed between 0 and R. Between 0 and R, Q enclosed is equal to a fraction of the total charge. The total charge of the entire sphere is big Q. What's the fraction? Fraction is the charge inside a sphere of radius small r versus the charge of the entire yellow sphere of radius a. We know it's proportional to volume, right? Charge is proportional to volume because the charge density is the same. So I would write r to the power 3 divided by a to the power 3. Because the volume is in turn proportional to r, the radius to the power 3. Right? And if you plug that in, you get E equals to K Q a to the power 3 times r. Right? This is the result that we already saw in our video lecture. This is inside the sphere. So the field increases linearly. And I can even put an arrow here to indicate the direction of the E field. So the E field grows linearly from 0 to at the center to the surface. Okay. But let me ask you this. if this is not an insulating sphere, rather it's a conducting sphere, does that, so what is the field inside? What would the field inside be equal to if it's a conducting sphere? In a yellow part, if it's a conducting sphere.
On the inside of the sphere.
Yes.
Let's see. That's just the KQ over R squared, right?
We're talking about inside a conducting sphere. This yellow sphere is a conductor. What is the field inside that sphere?
I thought that was 0, right?
That's right.
Zero is
Yes,
vector
yes,
zero.
yes. The field inside any conductor, any shape, is 0. Okay, that is not Gauss's law, but that is required for an ideal conductor. Okay, very good. So it's not 0 right now because it's not a conductor, it's an insulator. Okay, now what about the region between A and B? So in this vacuum part, okay, between A and B, between the shell and the solid sphere, how do you calculate electric field there? Well, again, I can draw a Gaussian surface, right? This time the Gaussian surface would be something like this, right? Be something like this, right? Of radius r. Okay, and you still have the same symmetry, so you can follow this exact same steps: 1, 2, 3, 4, and 5, right? You know, the exact same steps because it's followed the exact same symmetry. The only difference is the charge enclosed is how much this time. We're looking at a Gaussian surface like this. How much charge does it enclose? That's not a hard question, is it? How much charge? I'm sorry?
Would it just be Q? Or?
That's right, just big Q. So this time the total charge enclosed is big Q. Okay, it's not this, it's just big Q. So now we have, so this is between 0 and A, but between A and R, between A and B. Okay, between A and B. So Q enclosed this time equals big Q. That's it. Okay, so therefore E equals to what? K Q over R squared. That's it. Okay. So this becomes the electric field of a point charge once again. But you see, it's different from the first expression. The first expression is linear growing. This one goes like over R squared. Okay. Now let me ask you, this expression here, will this expression change if the sphere in the middle is a conductor instead of an insulator? Does that change this answer?
No.
No, it doesn't, because you still have the same symmetry. Okay, as long as you have the same symmetry, which is spherical symmetry, you know, I don't care. How are they spherical symmetrical? Are they uniformly distributed or are they only on a spherical shell? I don't care. As long as you still exhibit spherical symmetry, you would have this general formula, the same general formula, and the only difference is how much charge is enclosed, and the charge enclosed is the same. Okay, so yeah, you wouldn't know whether you have a conducting sphere in the middle or insulating sphere in the middle. Okay, very good. Now let's look at this region here between B and B plus D. Looking at this region here. You're looking at this region here. Okay, what is the electric field there? Now, I have to tell you what this is. This is a conducting shell of thickness D, okay? So inside a conducting shell, what is the electric field equal to?
0.
How much again?
0.
0, yes, that's right. And look, it's inside the conductor, it's gotta be 0, no matter what, okay? So, so between B and B plus D, E equals 0. That's it, just conductor. Okay, now finally, looking at somewhere outside here, you are here. What is the electric field at this point? Okay, so this time you're outside the whole setup, but you still have spherical symmetry because the entire setup is spherical symmetrical. So you can still do the exact same Gaussian surface approach. You will end up with 1, 2, 3, 4, 5, all these 5 steps remain true because they only depend on the spherical symmetry nature of the problem, which is still the same. Okay, so the only difference, again, is how much charge do we enclose? Okay, so how much charge do we enclose? So that was 0. Okay, this time you are here, right? The Gaussian surface will be something like this, right? How much charge does it enclose? This Gaussian surface right here. How much charge does it enclose?
Q and Q.
That's 2Q. That's right. Very good. So Q enclosed. So R greater than B plus T. Q enclosed equals 2Q. So E is equal to KE 2Q over R squared. Okay? That's how we do it. Right? So again, for all spherical symmetry, you have the same generic expression for the electric field. It's the same for anytime you have spherical symmetry. The only difference is how much Q enclosed is equal to. That's different for different regions. Okay, and of course, we also realize that inside an ideal conductor, the field is 0 anyways, no matter what. Okay, now as an added question, let me ask you this. You know, there's a total amount of charge Q on the conducting shell, right? On the conducting shell. Where are these charges? Can some of the charge be somewhere here, for example? Is that possible? No, because it's inside in the solid part of the conductor. That's not possible. So no. Where can they go?
Outer surface.
To the outside. The
Outer surface. So you mean here? Is there anything on the inner surface at all?
No.
Normally the answer is no. You don't have any charge on the inner surface. Okay, let me. So here you have a conductor, right? And just some extra charge, you know, on the outer surface. Okay. And we argued in my video lecture that even if you have a hole here, a cavity here, okay, so you have a solid part, which is this part. That's the solid part. But that's a cavity in the middle. There cannot be any charge here. There is no charge here or here or here. That's not possible. We argued that. However, there is an exception to this rule. What if you have a charge here inside? See, we have a charge Q here. Is there still no charge on the inner surface? I mean, how come we know there was no surface, no charge on the inner surface? It was because we drew a Gaussian surface. Remember that? We drew a Gaussian surface like this, right? Now, this red Gaussian surface is entirely within the solid part of the conductor. So what is the electric field anywhere on the red surface? Tell me.
0.
0, equal to 0, no matter what. That means the flux got to be 0 because the electric field is 0, the flux also be 0, right? If the flux is equal to 0, how much charge must be enclosed by this red surface? But remember, flux equals to Q enclosed over epsilon naught. Flux is 0 for this red surface because the E field is 0. And therefore, how much charge is enclosed?
0. Q
0. So do you still believe that there is no charge on the inner surface of the conductor this time? If there is no charge inner surface, then don't forget there is a charge here, right? I mean, it's already there, right? Then what would be the total amount of charge enclosed?
Just Q.
That would be positive Q. Is that possible? No, because the total charge enclosed must be 0 because the flux is equal to 0, right? So therefore, if you have a charge in the cavity, that changes the game. Okay, the inner surface of the conductor this time must be charged so that the total charge enclosed by the red surface is still 0 because the flux is 0 through the red surface. Okay, so tell me, how much charge must be on the inner surface now? On this inner surface?
Is it negative Q?
Negative Q, that's right. Okay, so going back to our problem, you must have a negative Q. This Q is the total amount of charge enclosed. Okay, you have a positive Q here, so on the inner surface, you must have negative Q. You must have negative Q. Negative Q. Okay, so tell me, because of that, how much charge must be on the outer surface then? On the outer surface
Positive
I'm sorry, positive what?
Q, or would it be 2Q?
Positive 2Q, yes. 2Q, because the total charge is Q. Okay, I have deposited some net charge on the shell, the total charge is Q. And then out of that Q, negative Q goes to the inner surface and positive 2Q goes to the outer surface. Total charge is still Q. Okay, so that last part of this problem is based on a combination of Gauss's law and the ideal conductor argument, which is to say that the electric field is zero anywhere in this region. Okay, so that's where the charges go. Now, of course, if this shell is also an insulator, that doesn't satisfy that rule. The electric field inside the insulator can be non-zero. So you can put any charge anywhere you want and they won't move. That's why they're insulators. They cannot move. The charges cannot move. Okay, but if it's a conductor, then, you know, to make sure that there's no electric field inside the shell and at the same time satisfy Gauss's law, you don't have a choice. And that is, you must have an equal amount of negative charge on the inner surface to cancel with the positive charge here. Whatever left over goes to the outer surface. Okay, so that's something to keep in mind. All right, so problems like that, I've given that to my previous 1C midterm ones. So it's really, you know, just still spherical symmetry, but you have a little bit more complication. You have concentric spheres and shells. Okay, so that was the first problem. And now we have a second problem to consider. That's cylindrical symmetry. I didn't even draw the charge distribution because I want you to consider multiple possibilities. Let's say you have a, so this is the, you have a cylindrical shell, you have a cylinder in the middle. Okay, you have this cylinder in the middle. Okay, it could be a solid cylinder, could be a cylindrical shell. Okay, let's say it's a solid conductor. Okay, this yellow part is a solid conductor. The total charge per unit length is lambda. Okay, and I surround it with another solid, cylindrical shell concentric with it, and the charge is negative lambda per unit length. Okay, can you find me the electric field anywhere that is, you know, starting from center here between 0 and A, between A and B, and then greater than B? Can you find the electric field? You know, it's just the same as cylindrical symmetry that we discussed in the video lectures, except this time, again, you have two sources, okay, they're concentric with each other, okay? The idea is similar to this problem, except we need to draw a different Gaussian surface. So what shape of Gaussian surface do we draw this time?
Cylinder?
Yes, you have to draw a cylinder concentric with these two cylinders. Okay, so for example, if I want to know the electric field, if I want to find the electric field, let's use a different color, of this point right here, how would I do that? Well, then I would draw a Gaussian cylinder which passes through this point, but it's a cylinder. So it's you know, it's like this. It's a cylinder like this, right? I would draw something like this. Okay, because anywhere on that cylinder, the electric field is radially outwards, assuming lambda to be positive, and they have the same magnitude everywhere on that surface. That's cylindrical symmetry. Okay, and then I would write down Gauss's law passing through this surface as this. I would write E dot dA. Now, it's not just a side of the cylinder, there's top and bottom, but there is no flux going through the top and bottom because the electric field lines will be parallel to the surface of the top and bottom, so they don't escape the surface, so there's no flux. Okay, it's only on the side. That's the first step. I need to make sure. So first of all, it's the side. Only the side of the cylinder has flux lines going out, E dot dA. Okay, and the next step is, I know that E and dA are both radially outwards on the side, so I have just EDA. E and dA have the same direction, so it's just EDA. And the next step is that E, the magnitude of E is uniform. I take that E out, side, and dA. And of course, the next step is simple. I just find the area of dA, of this A here. A is a cylinder of radius R, so that's radius R. And the length, length here, I call it L. So it's just 2 pi R times L. That's the side area of a cylinder, right? So that's the flux. But wait a minute, what is that equal to? That equals the charge enclosed over epsilon naught, right? So therefore, I can then find the electric field at location R, and that is just equal to Q charge enclosed over 2 pi epsilon naught R, and then there's an L, you divide that off. Okay, so that's the electric field. All right, for different locations, the only difference is the charge enclosed. For example, inside the yellow conducting part, okay, so 0 less equal to R and less than A. What's the charge enclosed? Anybody? If it's a conductor. Again, we're inside an ideal conductor. What's the charge enclosed?
0.
Yes, 0. That's a conductor. So therefore, E equals 0. Of course, it's got to be equal to 0. We know that, right? Now, between A and B. So you're in the empty surface, empty region, okay, between A and B. So let me, if I were to draw a top view of this shape, I would look at something like this. That's the, okay. So we're looking at this region in the middle. We're looking at this region in the middle. That's the empty region. Okay. So here this is lambda. I'm sorry. This is lambda, and that's also lambda. But in the middle, in the yellow part, in this yellow part, it's empty space. What is the electric field in this empty space? That's what I want to know. Again, you would draw a Gaussian surface. This Gaussian surface, let me use green color for the Gaussian surface, will be somewhere here, like this, right? Okay, so let me draw that. So that's the Gaussian surface. Radius is R. Okay, and I can apply the same argument that I did here to lead to the same exact general answer. But what is the charge enclosed by this green Gaussian surface? By this green Gaussian surface that I just drew right here.
Lambda now.
Yeah, it's lambda per unit area. Now, per unit length, I'm sorry, but the length is L, right? I used L here, right? The length is L here. So therefore, the charge enclosed is lambda times L. Again, lambda is per unit length. The length is L, so lambda times L. Okay, and therefore E equals what? Q over L. Q is lambda times L, so Q over L is just lambda. Lambda over 2 pi epsilon naught R. All right, that's between A and B, and that's the same answer that we got for for an infinite long wire of length L, of uniform charge density lambda per unit length without that outer shell. The only difference that we have, addition to that, we have an outer shell here. An outer shell here. But does that change the answer? No, because that doesn't change the symmetry of the problem. Okay, so the answer is the same for the electric field between A and B. But once you're outside, once you're here, you're outside everything. Okay, how much is the electric field there? Well, that actually, this is a negative lambda. Okay,
Professor,
you have to draw a Gaussian surface like this, right?
For inside, would the flux be equal to Q over epsilon naught for what we were just talking about?
Yeah, the flux is equal to Q over epsilon naught. That's
Okay.
right.
Thank you.
Yeah, but Q is lambda times L. That's why you have this answer. Okay,
Right.
now so for if looking at electric field there, you're going to draw a Gaussian surface like this, right? Like this, right? And for this Gaussian surface, how much charge does it enclose?
2 lambda per L.
There is lambda and there's negative lambda. I made a negative this time.
Oh, okay.
Yeah, so what's the total charge enclosed?
0.
That's right. Q enclosed equals lambda plus negative lambda. That's just 0. Okay. Times L, actually times L. It's 0. So E equals 0. There's no field. The field of the shell and the field of the cylinder just cancel each other out outside. Okay, so you see, there's very little algebra. I mean, there's very little integration you have to do. It's as simple as it gets. So that really, highlights the power of the Gauss's law. You try to solve these problems without Gauss's law, using Coulomb's law. I mean, you're gonna have to do a lot of integration, right? In fact, we did that, for a uniformly for a very long while. We did that. We even extended that to go to get the electric field of a plane. Now, I don't have time to go over the electric field of a plane, but we went over that in a video lecture. That's the third of the 3 symmetry cases. And by drawing a Gaussian box, you can easily find the electric field. Again, with very little calculation, you find the answer to be sigma over 2 epsilon naught. Remember that, sigma over 2 epsilon naught. Oh, by the way, the field outside an ideal conductor is sigma over epsilon naught, not 2 epsilon naught. Okay, so again, the field outside an ideal conductor is sigma over epsilon naught. The electric field above or below a very large flat plane is sigma over 2 epsilon. There is an extra 2 here. And you can get both answers using Gauss's law, of course. But there's an extra credit problem that I assigned. That extra credit problem is like asking you to derive the expression of the electric field outside an ideal conductor. You want to show why it is equal to sigma over epsilon naught without that 2 in the denominator. You are not allowed to use Gauss's law, otherwise this is too easy, okay? We already did that in a video lecture in the textbook. I want you to show that result without using Gauss's law. What you're allowed to use is the result of the electric field above and below a very large flat plane, which is sigma over 2 epsilon. There's a 2 here. I want you to show why. What happened to that 2? How come it disappeared when you don't have just a flat plane, rather you have an ideal conductor? Okay. A lot of people can give me the correct answer, assuming that this ideal conductor is basically just a slab of certain thickness. Okay, so you got 2 parallel surfaces, basically. No, that is not adequate. I want you to show that for any shape. You can have an ideal conductor of whatever arbitrary shape. How do you find the electric field right outside of it without using Gauss's law? That's the extra credit. Okay, as extra credit, I cannot give you any hint. It's all your own work. The only thing I can tell you is that there is very little calculation. If you started to use a fancy integral, no, it's not a fancy integral, okay? It's just, there's a clever argument. And that's something you want to think about, okay? So that's my, extra discussion problem for chapter 24. Do you have any questions, or you want me to solve any extra problems or anything before we get on to the lab today?
I just had a question about this problem that we just did. So if we're talking about like a point like between A and B, then would it be like influenced by, wouldn't it be, why is it not influenced by both like lambda and negative lambda both sides?
You're looking at between A and B, so we're looking at a point, say here, right? A point here, right?
Oh yes, or yeah, along like the green circle inside. Yeah.
Yeah. Oh, I'm sorry. You're right. You're right. Let me erase that. You're looking at a point here, right?
Yes.
Okay. This Gaussian surface, it encloses this charge, but it does not enclose that charge. Do you agree?
Yes. I see.
So yeah, because it has to be enclosed, has to be bagged by that Gaussian surface. Okay. The only thing you bagged is that cylinder. You didn't bag that shell outside. Okay, so that's why the charge that enclosed is lambda times L.
Thank you.
Yeah, good. Any more questions, folks? Okay. If you don't have anything immediate, you can always ask me later. Okay. If you want to stay behind after the class, you ask me some extra questions. I'll be more than happy to entertain your questions. But if you don't have anything immediate, let's move on to today's lab. Okay. This lab is called Gauss's law, and let me share a new screen with you. New share, hold on. So we're gonna stop this share. I'm gonna share a new screen. Gauss's law. Okay, so this is the lab. If you studied the lab manual for this lab, you realize that we're not really studying the exact Gauss's law. The exact Gauss's law deals with the electric flux. So we're talking about the electric field. Okay, we're not measuring the electric field. You know, as funny as it sounds, this E&M course, we do a lot of labs on E&M. We never once measure the electric field directly. We measure something else, okay? We don't measure the electric field. And we do measure the magnetic field, but we do not measure the electric field. This lab is no exception. We're not measuring the electric field. We're measuring something, which is not quite the electric field, but the idea is the same as the symmetry argument of Gauss's law. Okay, the quantity we're measuring is the intensity of light, not the electric field. So in this sense, you cannot say we're doing Gauss's law lab, but we're doing an experiment in the same spirit of Gauss's law when applied to symmetry cases. What's really important is not the electric field. Rather, it is how we use symmetry argument to find a certain quantity, how it depends on the location. Okay, so how do you define intensity? As you recall from physics 1B, intensity is power intercepted per unit area, right? Power intercepted per unit area. So suppose I have a point source of light. It emits power in all directions uniformly because it's just a point, right? There's no structure, so it's got to be spherical, symmetrical, okay? And if I were to draw a Gaussian surface centered at that point of light, a point source, a Gaussian sphere, okay? Then how much total power does it intercept? Let's say it's P, okay, the total power intercepted is P. Now let me ask you, does this P depend on the size of this sphere? In other words, I'm using a bigger sphere, would I intercept less or more power?
Less power.
Why do you intercept less power?
The unit area has grown, so that.
Okay, so you're talking about intensity, which
Yes.
is power per unit area.
Right.
Power is just total amount of energy that you intercept per unit time. Okay, that's power. Do you believe the power to intercept will depend on the size of the Gaussian surface?
No, it's just like a vector pointed radially out, right?
Let's say the light emits, this source, this little light bulb emits 10 joules of energy per second, let's say, okay. I'm gonna intercept 10 joules of energy if I have a sphere with no holes on it, right? It doesn't matter how big that sphere is. You're gonna intercept total amount of which is 10 joules per second. Because the power is independent of how big a sphere you use to intercept, as long as there's no hole. Okay, the P is the same. But if, just like you said, if the area is smaller for that sphere, the power will be more concentrated, so the intensity will increase. Right? Intensity is power divided by area. And since the intensity is the same everywhere on that sphere, why? That's symmetry. Okay, you have a point source in the middle of a sphere, and everywhere on that sphere, the intensity must be even, right? That's symmetry. Okay, so how much is the intensity now? Total power divided by total area. That's the definition of intensity. Area is 4 pi r squared for a sphere. So therefore, intensity is P over 4 pi r squared, okay? And what happens if the area of the radius r increases? Intensity goes like r squared, 1 over r squared. So the intensity must grow, must decrease as inverse squared law. Okay, that is because of the symmetry of the problem being spherically symmetric. Okay, so this is not electric field. We're talking about intensity, but using the same argument of symmetry, we can see the intensity must diminish as 1 over r squared if it's a point source. Okay, what if it's a line source of light? Let's say you have very, very long, imagine you have a very, 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 very long fluorescent tube of light, infinite long, with uniform brightness everywhere. You can imagine light beams will go out like this, right? So this time, if I want to find intensity, how would I do that? What kind of Gaussian surface would I use this time?
Cylinder?
Yes, it's going to be a cylinder centered on that fluorescent tube, right? And everywhere on that cylinder, on the surface, at the side surface of the cylinder, intensity must be the same, again, by symmetry. But this time, as you grow the radius of the cylinder, you'll find the area goes like, it's not 4 pi r squared. No, it's 2 pi r times L. Okay, 2 pi r times L. L is the same as you grow the radius of the cylinder. So this time, the area grows like r, not r squared. And therefore, instead it must drop like 1 over r, not 1 over r squared. Just like the electric field will drop like 1 over r, not 1 over r squared for a very long line of charge. The same argument, symmetry argument, leads to the same answer, whether it's the intensity or whether it's the electric field. Okay, and the last example is a plane. Let's say you have a very, very large, infinitely large computer screen. Okay, infinitely large computer screen with uniform illumination. There's no content on it, just blank. It's super white, but it's the same brightness everywhere. In infinitely large, this computer screen, infinitely large. Don't you like that, right? Okay, and then imagine you measured intensity, how bright light is. As you move that probe away, do you see any diminishment in the brightness? You shouldn't, because imagine you draw a Gaussian box. You could increase the height of this box by moving away from that screen, okay? That doesn't change the top and bottom area of the box. And therefore, the concentration area does not change, does not increase or decrease. Therefore, you intercept the same amount of power over the same amount of area. So the intensity, which is power over area, stays the same. Okay, that is very interesting because that means that when you have, let's say you have a light bulb, which is 500 watts, or maybe it's too bright, let's say 200 watts, okay? If you put that light bulb at the center of your ceiling, just one light bulb, then immediately below that light bulb, it's very bright. But at the corner of the room, it's not very bright at all because you're pretty far from the light bulb. Because the light bulb, the intensity goes like 1 over r squared. You're pretty far from light bulb. But instead of this one light bulb of 200 watts, you use light panels, which totals 200 watts, but evenly distributed over the entire ceiling. You can think of this as a very large plane of light source. Now, this time, as you move away from the ceiling, do you see a big drop in brightness? No, you don't, because looking at basically a plane source of light instead of a point source. This is the reason why, if you look at, you go to any large hall, public hall, you look at how they distribute light, they don't have a single light bulb in the middle. No, they have light bulbs evenly distributed, or better yet, the panels of light. And that's because that way, distribution is more even. And when you get very close to the ceiling, you don't get burned. When you get far from the ceiling, it's still very bright. It's quite even that way. Okay, so that's the basic idea. So how do we do the measurement? Well, again, there are 3 cases, okay? In the actual lab, PCC lab room, we would use a light bulb, a really small light bulb for the point source, and we use a fluorescent light tube, which is, in our case, it's about 3 meters long. It's a pretty long light tube. Yeah, 3 meters long for the line source. But you may say, oh, but 3 meters is not infinity. I'm sorry, we don't have an infinite long light tube, okay? We have 3 meters. How is 3 meters equivalent to infinity? Well, sometimes 3 meters is very close to infinity. Why? Because if you choose at the midpoint of that tube and you move just a little bit away from the tube, say a couple of inches, that distance is a lot less than 3 meters. So with that little distance, the thing looks almost infinite. Okay, so that was the case for the line source. And then for the plane source, what we used was a computer screen, literally a computer screen. We used the biggest computer screen we could find, which is about like 17 inches, okay, about 17 inches, and we turned it into a totally white screen, okay, as bright as it gets, like maybe an empty Microsoft Word document or whatever. And then we take this light, we have this intensity photometer. We actually take that probe and we gradually move away from the screen. We want to see whether the intensity drops or not. I mean, it's going to drop at some point, but it doesn't drop appreciably as it moves away, just a little bit away from. So those are the things we actually did in the PCC lab room. Of course, we're not in the PCC lab room, so what we can do is for the point source, instead of using a physical light bulb, we are going to use we're going to use a virtual lab pivot interactive. Okay, for the other 2 sources, unfortunately, I cannot even find a virtual lab. So what I have to do for the other sources is I just give you data. See here, just give you data. Somebody else did in a PCC lab room. You use these data. Okay, so what do we want to do with these data? First of all, what data do we collect? Intensity as a function of distance to the source. Okay, I versus R. Collect multiple times. Okay, but what do we do with this data? Now we know that I should go like constant over R squared for point source, should be a constant over R for line source, should simply be just a constant for plane source. Those are the theories. How do you test these theories? Well, we're looking at a power function, right? R to the power -2 or R to the power -1. These are power functions. You can turn a power function to a straight line mathematically. How do you do that? Anybody? How do you turn a power function to a straight line?
With logarithms.
That's right. Taking a natural log or any log of both sides. So you start with, I equals constant times R to the power n. You take natural log of both sides. Okay, and then you, instead of plotting I versus R, which would be a curve, right? If you plot natural log of I versus natural log of R, you can get a straight line. And the slope of that straight line is that power n you're looking for. Okay, so that's something we can test. We find data of I versus R, and then we plot natural log of I versus natural log of R. Do you get a straight line? Is the slope of the straight line the same as theoretical prediction? Should be -2 for a point source, should be -1 for a line source, should be 0 for a plane. Those are the theories. See how close you get. Okay, again, for the line source and the plane source, you're just going to use these data. Take the log and do the plot. Okay, but for the point source, I did find a pivot interactive lab, and here is the Joly photometer. So let me bring that up. The Joly photometer lab in pivot interactive. So I'm going to do a new share. You can see it, right? The pivot interactive, right? Okay, so what's a Joly photometer? A photometer is a device that measures the brightness, measures the intensity. Okay, so here is how this thing works. So here's a video that shows how this thing works. Okay, you use a piece of wax, which is translucent. Okay, this is a piece of wax, translucent. Okay, and then you have a piece of wax. You also have what he has in his hand is a piece of tin foil, which is opaque, all right? Which is opaque. Light cannot go through that. So watch what he does. Okay, place on that. All right, now you have two pieces of wax with aluminum foil in the middle to block the light transmission from one side to the other. Like this, okay? Now, watch what happens. There's a light source here, and there's another light source there, right? The wax is translucent. So if this side, if this piece of wax is closer to this light bulb, it's gonna cause it to be brighter. You can see it from the side because of the diffusion of the light. But as you get close, as he moves this to the other side, and then you find that that side becomes brighter because it gets closer to that source. Okay, so watch. You see here, this side becomes brighter, see that, because it's getting closer, but this side gets darker because it's further away from the source. Okay, so that's the idea. That's the so-called Joule photometer. But how does he use that to measure the brightness, the intensity of a point source? That's in the second video. So look at the second video, okay? In the second video, there are two light sources. This one is a reference. The one on the left is reference. It doesn't change. There's only one light bulb of the same brightness, same intensity. I mean, the same power all the time. But the one on the right is variable. The one on the right, it's LED. LEDs have different number of beads. You can have 1 bead, 2 beads, all the way to, in this case, like 9 beads. So you can adjust the power output of this LED. Okay. So watch what happens. Right now, I have 1 bulb. See that 1 bulb on the lower left corner? I choose 1 bulb. So there is no 1 bulb here. It's not very bright. Now, right now, you can see here, the left side of this piece of wax is brighter than the right-hand side because the left-hand side receives greater intensity from here. It's very close. But as you move this piece this way, the brightness of this side is going to diminish. The brightness of that side stays the same because this distance never changes. Okay, this distance never changes. At some point, when you move further down, at some point, you find the left and right side have the same brightness. The same brightness. And that's a data point you should take. So for 1 light bulb here, you'll find that, let's say this R1 equal to say 30 centimeters. So at 30 centimeters, you'll find that the two sides are the same brightness. That's a data point to take. So watch. Okay, you see the brightness of the left-hand side diminish, the right-hand side stays the same as you move away. Keep on going, keep on going, keep on going, keep on going. Somewhere here, see here, the left and right side, they almost have the same brightness. Maybe I should go a little bit further. There we go. See that? Agree? That's pretty much the same now. Okay, so how far is that distance? Well, you deploy a ruler, you can measure that distance. Okay, you can measure that distance. So there's a certain distance. You know, you can go from, say, the center of the light bulb to the center of the left side of the wax. You know, that's a distance. You measure that. Okay, so that is for 1 light bulb on the right side. Now let's change to, say, 4 light bulbs. Okay, so load that. This time, this is brighter. This is 4 times as 4 times more power. So therefore, this side is brighter than before, right? So therefore, if you move away from this source, you cannot move that far down anymore because the right side is brighter than before. To match the brightness, you cannot go too far from this light bulb. Otherwise, you cannot match the increased brightness on the right side. So watch. Somewhere here, see somewhere here. You didn't go that far, did you? Right? So that's for 4 light bulbs. Now let's try, say, you can go all the way to 9 light. Let's say try 8 light bulbs. This time, this brightness is even greater. Therefore, you cannot go that far. You have to go. You have to stay closer to this guy to match the brightness. So let's watch. See here, somewhere here. See that? So at this distance, the 2 sides have the same brightness. That's for 8 light bulbs here on this side. Okay, so take a data point reading for each number of light bulbs. There are 9 of them, 1 through 9. Okay, And what's the data analysis? Here is how I do data analysis. Hold on. Let me do this new share with you. Let's do the new share. Safari. Okay, let's go back. Okay. In going back to the case of the think of the light bulb as a point source. It's not really a point source, but we can make this approximation. I equals power emitted divided 4 pi r squared, right? 4 pi r squared. R1. This 1 means there is one light bulb on the right hand side. One light bulb on the right hand side. Okay, that's what we call it R1. So that's the intensity is I. Okay. So at some point, value of R1, the intensity of both sides match. Now, what if you have 2 light bulbs? Then the intensity becomes 2I, right? The K equals 2 because you got 2 light bulbs. Okay. And at what distance to the left light bulb should you stop to find a match between the 2 brightness? That's R2. That's K equals 2. R2. That's 2 light bulbs. Then you do the same for R3 with 3 light bulbs, R4 for 4 light bulbs, and so on. Okay. And then this is the general formula. K is equal to 1 through 9 for the number of light bulbs. You take the natural log of both sides and you go from there. Okay. And this N ideally should be 2, right? Negative 2 here, right? But in general, we just call it N. We just call it N. N should be equal to negative 2 ideally. When you do this plot of natural log of K versus natural log of R sub K, you can find that slope that equals ideally negative 2. See whether that's the case or not. So that is the only part where you have to take the data yourself. Okay. The other 2 parts, line source and plane source, you just go ahead and find, use these data to do the log versus log plot. Okay. Let's see if there's a question. All right. Very good. Any questions, folks? Okay, I see somebody posted, John, thank you for posting that link to the plane source. Thank you. Okay, any questions? Again, this lab, is that clear what I wanted? Okay, by the way, when you look at the Pivot Interactive, you have the videos, and after the videos, they sometimes give you some assignments, like I have to plot this or whatever. You can ignore these assignments, okay? You do only what I ask you to do in this, in my lab instructions. The only thing we want from the Pivot is to use their videos to do data, to take some data. That's all we do. We don't use the data analysis. Okay. So, did I explain everything? All right. So if you don't have any immediate question at this point, I'm going to stop recording now.